All right, good morning once again. Quick review of yesterday. Yesterday we talked about spring potential energy. The whole concept of potential energy is you have a system that's in a particular state where if you trigger it in the right way, energy is released. So that could be chemical potential energy in food, or chemical potential energy in some chemicals that are going to undergo a reaction. It could be nuclear potential energy stored within a lump of uranium that's radioactive. It could be electrical potential energy stored in a battery that you buy from a store. Or it could be gravitational potential energy stored in an object held above some point that it can fall to, like a pendulum or a piano lifted above the floor. Or it could be spring or elastic potential energy. So spring potential energy and elastic potential energy are essentially the same thing. And the reason why spring potential energy exists is because there's a force that the spring will exert on the mass if you somehow release it. So I'm not going to do this because I'll hurt myself, but if I take this spring and I pull it like here to this point and then I let it go, obviously it's going to do work to this thumb if I let it go with this hand. And since it has the ability to do work, there must be some kind of energy stored in the system when it's in this state. That's called spring potential energy or elastic potential energy. It really doesn't matter. In terms of calculating things, Hooke's law says that the force that the spring exerts on a mass that is stretching it, or the force that the spring exerts on whatever is stretching it, maybe it's my hand, is equal to the negative of something called the spring constant times the displacement. When I take this spring, I'm not going to do it horizontally. I'll just go with this vertical spring that's hanging here. When I apply a force on this, and there is a force being applied to the spring right now, it's the force of gravity acting on this 500-gram mass. The force being applied to the spring is downward, but the force that the spring exerts on the mass is upward. So there is a force on the mass upwards, and the displacement, look at the length of the spring here. Now look at the displacement of the mass. The displacement is towards the floor. So the displacement is downward, but the force on the mass is upward. The force by the spring on the mass is upward. That's why that negative is there, but we had this conversation yesterday. Look, if you just want to know the force that's involved, how many newtons of force are in action at that particular point, then it's equal to kx without the negative sign. We then went through a process that led us to a formula for spring potential energy or elastic potential energy. And I don't have a preference. Sometimes I will say elastic potential energy, sometimes I will say spring potential energy. Whether I'm talking about an elastic band or a metal spring, it doesn't really matter. This is equal to 1/2 kx squared. So what we are going to be doing today is going over any questions you have, and then you're going to have a lab to complete, and it's going to be a lab much like the pig lab in that you have a goal to find. But in the pig lab, would you agree you were trying to determine the acceleration due to gravity? So you could look at your answer and see how close you get. Your job today is with a partner to find a spring constant, but the simple fact of the matter is you don't know what the spring constant is. I do, and all of the springs are different. So you can't necessarily ask somebody else in a different group, well, what did you get? When you look at all of the springs hanging from the ceiling, there's a little piece of masking tape attached to the bottom of them with a letter. So you can think of this, what we're going to be doing later today, as a lab exam. You have to collect data, do an experiment, do an analysis. Can you stop that, please? Thank you. Do an analysis to determine the value of K for a spring, and part of your mark is going to be what you got. Okay. I'll talk more about that later. In the meantime, let's talk about any questions you have from the additional problems that were assigned. Any questions that anybody has? Yeah. Number 6. So an experiment is performed to find the spring constant of a spring. Oh, this is how fortuitous, because you're going to be doing an experiment today to determine the spring constant of a spring. I would say that these students did a less than stellar job of designing their experiment. They only have 4 data points. I've always said the magic number is 8, and when you do your lab today, I'll help you out with how you're going to collect 8 data points. But anyway, we get 4 data points here. They've applied a force. It doesn't actually say that they hung a mass to a vertical spring, so maybe they just taped one end of the spring to a tabletop and hooked a spring scale and Newton scale to it and stretched it and read how many newtons of force it was and determined the displacement of the spring. Using your graphing calculator, determine the values of the spring constant. Well, what are we talking about here? We're talking about Hooke's law, which says that for a spring, if it obeys Hooke's law, and these springs do, when you plot the force as a function of the displacement, you should be getting a straight line. Now, that line may not go through the origin in your experiment, and it may not go through the origin in this hypothetical experiment. So you don't want to force the data. If I gave you graph paper, Nate, we would have to plot these points and take a ruler and draw the line of best fit. Okay? We're asked to do this on our calculator, though. Okay? For your lab, I'm going to want a paper graph. So how would you do it on your calculator? Your calculator is a way of doing it so that it takes the, what's the word I'm looking for? It takes the guesswork out of drawing your line of best fit. So let's enter the data first. When you turn your calculator on, you need to get into the area where you have your lists, and that's found by going Stat Edit. And you need to remember that your X data goes in your L1. So we want the displacement to be in L1, so we can enter 0.097, 0.149, 0.21, 0.245, and double check all of the entries. They look okay. For Y, we're going to put the force, because on my graph that I want to look at, the force is on the vertical axis, so 1.96, 2.94, 4.01, and 4.91. And you know, you just step back, look at your calculator, make sure everything is entered correctly. I think it's fine. Now, listen, you don't have to do this next step to answer the question, Nate. But I want us to. Let's look at the graph, okay? So, I'm sure we've talked about this before, but some of my classes, we do a lot of the same things, so I could be confusing this class with a different one. Go to Y equals and make sure there's nothing in there. When you graph things on your graphing calculator, you can graph functions, like you can graph Y equals X squared and put Y equals X squared here and look at the graph. Your graphing calculator can graph functions, or, are you with me? Or it can graph data. So in order to graph data, you have to enter it into your lists, which we've done. But then instead of going Y equals, you go second Y. And that takes you to the arena in your calculator where you plot data. And this will be useful for your lab, because I'm going to get you to do it on paper, but I also want you to take a look at it on your calculator. You'll notice that all of my plots are off. Plot 1, plot 2, plot 3, etc. is off. So I go into plot 1 and I hit on. What have I got going on here? I want individual points. I don't want the calculator to connect anything. I want X in L1 and Y in L2, and I want data points. So this is on now. Now, just a quick question. And I didn't ask it, but we did this morning in Physics 30, and it came up. Is anybody missing L1 and L2? Like, does your table list start at L3 or L4 or something? If you're ever missing L1 and L2, you need to reset your RAM on your calculator, and it will bring it back. Okay. So now, if I were to hit my graph key, I may not see anything. It doesn't look good. And the reason is that if I hit my window key, I happen to have window settings in there that I zoomed in or out to get in some other class at some other point in time. You don't want to try to zoom in on this data. You want to go window and enter your minimum and maximum values for X and Y manually. What is my X? My X only goes up to about 2.25. So for X min, I'm going to start at 0 and I'll go up to 0.3. I want a little bit more room. For my Y, my biggest Y is a little bit less than 5. So for my Y's, my minimum Y will go from 0 to 6. Does anybody remember what the scale does? X scale, Y scale? Yeah, it's where it puts the tick. So if I go from 0 to 6 with a scale of 1, I'm going to see 0, and then I'll see a tick at 1, a tick at 2, a tick at 3, etc. If I go from 0 to 0.3, my ticks, maybe I should change it to 0.1, or maybe even 0.05. But it's not going to change things. It's just, if I left it at 1, I just wouldn't see any ticks there. So now when I go graph, I can see the data. Now, would you agree that that's pretty linear? But the last data point doesn't look quite right? That's a visual clue to me to just go back to stat edit and make sure I've entered the data correctly. And I have. So what we would do is we would chalk up that data point, and I'll show it up here. We would chalk up that discrepancy to error. And if you were to draw a line of best fit, you would, well, I would probably draw it about like this. And I'm not looking at the origin, by the way. Okay? I'm not trying to hit the origin. I'm ignoring it, actually. So this would probably be how I would draw my line of best fit. Listen, can we ignore that fourth data point? I don't think we can, because there's only 4. If there were 8 data points and 1 was off, I would feel more comfortable ignoring it. But 1 out of 4 is significant. Now, we know that the slope of this line is equal to the spring constant. And again, I want to go through that. The reason why is that line has an equation of y equals mx. Our physics formula is F equals kx. So when you compare things, we're not rearranging for k. This is really important. I'm not rearranging this equation for k to determine what the slope is. I'm simply saying y is the force, x is the displacement, the slope must be k. So now we need to find the slope. Does anybody remember on your calculator how to do that? Jay? Right, we have to do a linear regression. So you go stat, you scroll over to calc. Are you with me, Nathan? Because you asked about this question. And then you scroll down to linear regression. Now, if you have a TI-83, you just hit enter. Any other calculator, you have to hit enter repeatedly to go down all of your choices. But what I end up getting for an equation is something with a slope of 19.5, which we would round to 20 newtons per meter. By the way, if I want to see the line of best fit on my calculator, I have to enter that in for y. There's a quick way to store it in there, but I'm not going to worry about that right now. So I can enter 19.502. I think if you went to 3 decimal places, it's going to be close enough. Times x plus 0.0373. Remember I said it doesn't have to go through the origin. There is a y-intercept here. And there might be a physical reason for it or not. It could just be error. And we go graph. When I compare that to this, wow, it's pretty much the same thing, isn't it? But it may not be as obvious next time. I'm actually quite impressed with myself. It's almost perfect, according to the calculator. Have I answered your question, Nate? Good. Any other questions before we get started today? Okay, so your problem today, and for those people that are absent watching this video, when you return, you'll be given hypothetical data, made-up data, and I'm going to want the lab report from those people as well. Okay. So your problem today, you can call it a lab exam if you like, but your problem is to find the value of a spring constant. Experimentally, that's the problem. So hanging from the ceiling are a bunch of strings with springs attached to them in a group of 2, or, I mean, if there's the odd person who wants to just do it on their own, that's fine, but I only have, I think I have 2, 4, 6, 8, well, I have 10, I think. I have 9 springs hanging, but I have room for a 10th. So I just don't want groups of 3. And we don't have enough for everybody to do the data on your own. You're going to determine the spring constant. So what it's going to involve is a graphical analysis. I'm going to want a graphical analysis where this is the force involved and this is the displacement of the spring. And what that means is that you're going to have to collect data. You're going to have to collect data for a force and collect data for a displacement. Now, you remember when we did some lab work where you had spring scales to measure forces? They're not ideal for measuring, are they? They're fidgety. So instead of measuring the force directly, what you're going to end up doing, since these springs are vertical, you're going to end up putting a number of different masses on them. So this is what you're actually going to measure. You will measure the mass that you put on there. Well, measure. You don't need to measure it because the masses are labeled, but I'll get to that in a second. And you will measure the displacement of the spring. I want 8 data points. Okay? And I will tell you right now that the mass sets that you have allow you to use the following masses, and I'll write it down in a second. 200 grams, 300 grams, 400 grams, 500 grams, 600 grams, 700 grams, 800 grams, 900 grams, and I want you to go to a kilogram. So you're going to actually get 9 data points here. You're going to start with 200 grams and work your way up in 100 gram intervals until you get to a kilogram or 1,000 grams. And I believe if I counted right, that will be 9 sets of data, which is more than enough. I don't know if this has come up. lab work in general is something that's very important in high school physics, like understanding error and understanding how to do measurements. If I were to start off with 200 grams, and this is a 200-gram mass, and I measure the displacement of that spring, and I'll talk to you in a little bit about how we measure that. And by the way, when you hang a mass on, things are going to start spinning, because when you take a spring that's a coil and you stretch it, there's a force involved sideways. There's a twisting force. So things will be spinning. But when you measure the displacement of the spring here, you will be measuring a relatively small distance. Okay. However, if I hang 600 grams, which would be a 500-gram mass with a 100-gram mass hooked to the bottom, pardon me, this is 700, this is 200 and 500. First of all, I don't drop it. I let it down slowly until I feel I can let it go. I don't want this thing bobbing up and down, because the forces involved will increase and it might pull it from the ceiling. Okay? But I know by testing these that 1,000 grams is doable. When you measure the displacement here, it's a larger distance. You're going to have an error in your measurement whether you're measuring this distance or whether you're measuring this distance. And the error is the same amount in all the measurements. The amount of error in this measurement is the same, but it's a more significant part of the total measurement. Your percentage error in your measurement here for small masses is going to be greater. And so I'm telling you that because when you have 200 grams to 1,000 grams and you finally construct your graph, if some of the data down here does not seem to jibe with the rest of the data, we'll have to have a discussion. I don't want to say you can ignore it totally, but you might discover that small masses produce questionable data. So what you are going to do is hang 200 grams from there. You'll write 200 grams down. Then what you're going to do is measure the displacement. Now, how do you measure the displacement? What is the displacement? Well, one of the things you're going to have to measure first before you put anything on is the length of the spring. Because your displacement will be a measurement from the top of the spring to the bottom of the spring compared to where it is now. Now, specifically, these springs look like the following. There's a coil of metal there, and then immediately there's your spring, and then there's a coil at the bottom that you hook your masses on. So what you need to do is measure this distance to begin with. That's the length of the spring. And the reason why we want to measure that distance is that when this is stretched, these two loops still have the same shape. What's being deformed is the actual springy part in between the loops. So if you and you want to measure things as accurately as you can, I'm not going to I don't mean to suggest that the number I'm going to give you is the number you're going to use. You have to measure it yourself. And I don't even have my reading glasses on. But let's just say you measure that to be 6.52 centimeters. By the way, all of your distance measurements should be to the nearest hundredth of a centimeter. I'm going to come back to that. You need to record that someplace, as well as your spring. So this would be spring I. So you would record someplace in your work spring I. And you would say the length of the spring is that. Okay, so now, when you put the 200 grams, when you put the 200 grams on here, now what you're going to do is measure from the top of that coil to the bottom of the coil. So with some mass on it, you're still going to have these two things, but it will be stretched out, And what you want to measure now is this distance. So how you're going to organize this in a data table is kind of important, because this measurement right here that I'm going to record is not actually the displacement, is it? If I measure that to be 14.63 centimeters, then x is going to be 14.63 minus 6.52. And since this is a measurement, it needs to be written down in your data table somewhere. I don't want you to just, in the lab, subtract that 6.52 and write down that answer. I want to see the length of the spring with no tension in it, and I want to see your data for the new length. So maybe when you set up your data table, you can put stretched length. And then you can have another column that's displacement, which will be your stretched length minus your at-rest length. Are you with me on that? Okay. Before I get to the analysis and what I expect, how are you going to collect all of these? Well, you have, in a mass set, you have 1,000 gram mass, you have a 500 gram mass, you have two 200s, and you have 100. You also have some 50 gram and 20 gram and 10 gram and 5 gram masses. That's not important. So if we start off with 200, well, that would be the 200. How would I get 300? Well, I have a 100 gram mass and a 200 gram mass. I can clip them together. That's 300. How would I get 400? It's almost like a little puzzle. 400 would be two 200s. How would I get 500? I'd use the 500. How would I get 600? The 500 and the 100. 700. 500 and 200. 800. 500, 200, and 100. So right now there's a 200 on there. I can clip 500. This is 700. I can add another 100 to it. And again, you're letting things down gradually. It's 800. How would I get 900? I take off the 100 and add 200. You get my drift here? It's possible for you to get all of those masses from 200 to 1,000, including 200 and 1,000, in increments of 100. And we don't want this to be happening. What's happening right now is it's oscillating. You want this to be, it can be twisting. This that's going on is called simple harmonic motion, and we'll do some lab work with that in the next unit. You want this to be as rest vertically as it can be. And that's a challenge. You know, you're going to have to sit down and have a partner hold the meter stick so 0 is there, and sit in a chair so you can really level things off. So that's how you collect the data. Does anybody have any questions about collecting the data? All right, so the analysis, what I want is a paper graph. You'll be given a sheet of graph paper, and each person submits their own work. So you're going to scale the vertical axis so you have your forces. I'm sorry, I guess I forgot one thing. How are you going to determine the forces? Jay? Right, it's the force due to gravity, because the force that the spring exerts is balanced by the force of gravity because it's stationary. So you have to take the mass in kilograms and multiply by 9.81 newtons per kilogram. So you will have the forces involved. If you go up to a kilogram, it will be 9.81 newtons. So you're going to have to scale your vertical axis so you can see all of those. You're going to have to scale your horizontal so you'll see your displacements. We're trying to find the value of the spring constant, which means you're going to be looking at the slope. You're going to be determining the slope on paper. We've done slope before. You're going to pick 2 points. After you draw your line of best fit, using a ruler, you're going to pick 2 points on your line of best fit that are not data points and are reasonably far apart. You'll find the slope to get an answer. What I want submitted And again, I wanted at a physics 20 level. Don't want something that looks like it was drawn and put together by a really smart 5-year-old. Okay? Big block letters. And I want it nice. What I need is a procedure. We can call this, I'm old school, it's called an experimental design. You know, how you do the experiment, including a diagram of the apparatus. So that if somebody was away, now if somebody is away, they're not going to collect their own data, I'm going to give them data. But if somebody was away during the whole explanation of how to collect the data, they could read your procedure and they would know exactly how to collect their data. The graphical analysis. Which means the paper graph done well, you've got a title, the axes are labeled, you've got a decent line of best fit drawn, you know, it's where it should be, and then right on the graph you can show your slope calculations. But I also want an explanation as to why is the slope equal to k. I want you to explain why in this graph the slope of the graph is going to give you the spring constant. I also want a linear regression equation from your calculator. And the value of k that it tells you. So I'm asking you, I mean, the slope of the line is k. It's what we're after. I'm asking you to do it on paper, but I also want you in your lab report that you're going to hand in to have something that says, when I entered the data into my lists, this is the linear equation that I got for the linear regression. So according to my calculator, this is the value of k. And I also want an experimental evaluation. What does that mean? How successful was the lab? Now we have an issue here because you don't know what k is. But that doesn't mean you can't evaluate the success of the lab. I mean, I really hope this is not going to happen with anybody, but if you plot your data and your data looks like this, and by the way, when you plot data, you put a point and you put a little circle around it. Like, they're really tiny. I'm drawing this large so you can see it. If your data looks like this, looks like a couple of googly eyes, I mean, that's fine. It's in a perfect straight line, but you might want to address why you're not getting a y-intercept of 0. And the only thing I can figure out here is, in this particular case, this initial distance from the top of the spring to the bottom of the spring was measured incorrectly. It wasn't the right measurement. It was only this much. So all of your actual data gets shifted a little bit. I hope you would agree that if your data looks like this, you better start to question what it is you did in the experiment. And you better address that in the experimental evaluation. I mean, I hope it doesn't look like that. Heaven forbid. I mean, if you just get something like this, I don't know. Maybe you just don't understand what it is you're supposed to be doing. Because we can clearly see the more mass you put on, the longer it gets. I don't know how you would get data like that. But the world is a strange place sometimes. So I do want an experimental evaluation. That's everything that I want. Okay? So while you guys are collecting your data, I will get some graph paper printed off, and I will put it at the front here. So the stations are all set up. Again, groups of 2 or single people. If we have to have a group of 3 because there's an odd number of people, I guess we can. I just don't want 5 groups of 3. Okay. Mask sets are at the back of the room. Be careful not to drop them. I don't want you to hurt yourself by falling on your foot, but maybe the more important thing is when these things drop, very often the hooks break off. So I have a whole drawer full of these with no hooks that I can't really use. Meter sticks are at the back. There are rulers up here for graphing, but I think you'll definitely need your meter stick to measure some distances. Okay? Pitter patter, in the words of my mom, let's get at her.